Okay, in this lecture, we're going to cover the second part of our section 3.7 material on improper integrals. So in the first part of this section, we had introduced the definition of an improper integral as a definite integral of a function over either an infinite interval or the definite integral of a function which has some discontinuity over our interval of integration. So that second type of improper integral is what we're going to be talking about in today's lecture. If we have a discontinuous integrand. So integrals where the function f of x, which we are integrating, has a discontinuity over the interval from a to b, is called an improper integral of type 2. And there's sort of three different cases that we could have for this type of improper integral. The first is if our function f of x is continuous on the interval from a to b, not including b, and let's say that it has a discontinuity at that right endpoint of our interval, x equals b. So in this case, we would define the improper integral of our function f of x over that interval from a to b as the limit of the definite integral of f of x from a to t, and then take the limit as t approaches b from the left-hand side. This is a left-hand limit here. So let's try to illustrate this and see why exactly we're taking a left-hand limit specifically. So here we were considering some function y equals f of x, which we were told is continuous on the interval from a up to b, but is maybe discontinuous at b. So let's say that we have something like this, maybe a function y equals f of x, which is continuous from a up to b, and maybe let's say we have a vertical asymptote for a discontinuity at that right endpoint b. So what we can do here is define the definite integral of this function from a up to some value t. So we would be talking about the area of this shaded region under the graph of our function from a to t. And we're then going to allow the value of t to approach b, but from the left-hand side. So since t is approaching b from the left here, that's why we've got our left-hand limit in our definition. So as we increase the value of t towards b, we're getting more of this area that we're interested in. And if that limit exists, we would say that this improper integral is convergent. So remember, when we're talking about improper integrals, we say that they are either convergent or divergent, depending on whether these limits that we use to define them exist. Now in part B, we have a very similar problem. Let's say that f of x is continuous on the interval from a to b, except at the left endpoint a, it is discontinuous. So then to define the definite integral of that function over the interval from a to b, we would take the definite integral of the function from t to b, and then take the limit of that value as t approaches a from the right-hand side. So again, to illustrate this, well, let's suppose in the xy plane, we have a nice continuous function on the interval from a to b. However, at this left endpoint, x equals a, we might have a discontinuity such as a vertical asymptote. So in order to define this definite integral from a to b, we could take the definite integral from some value t up to b, So that definite integral would be giving us the area of this shaded region under the graph of our function on that interval. And then we are allowing the value of t to approach a from the right-hand side. So since t is closing in on a from the right, that's why we're using a right-hand limit in that definition. So the closer that t gets to a, we can see that we're getting more area here. Now, in our third case, we could have a function f, which is discontinuous at some value x equals to c, which lies somewhere in the middle of our interval, between a and b. So in this case that we have a discontinuity somewhere within the interval rather than at one of the endpoints, we would define the integral of our function from a to b as the sum of the integral from a to c, where we have our discontinuity, plus the integral of our function then from c to b. So we would split this into two parts where our discontinuity is at either the left or the right-hand endpoint of our interval, and each of those integrals could then be evaluated using limits as we did in parts 1 and 2. And as long as both of these integrals are convergent, that is the limits for both of those improper integrals exist, then we would say the sum is also convergent. So to illustrate this, well, let's suppose that we have in the xy plane some integral defined on a to b, but at some point between a and b, let's say c, we have a discontinuity, say a vertical asymptote or something. So our function is nice and continuous except at this point c. So in order to define this, well, we would split up our integral from a to b as the integral from a to c plus from c to b, and then each of these would be defined using the idea that we had in parts 1 and 2. We could integrate from a to t, and then allow t to close in on c to calculate this area to the left of our discontinuity. And then we would add the limit of the integral from t to b and allow t to close in on c from the right-hand side to get the area of this region to the right of our discontinuity. And if both of those limiting values exist as we approach c from the left or c from the right, then the sum would also be convergent. It would be defined as the sum of those limiting values. So let's look at some examples working with improper integrals of type 2. So in this next example, we're asked to evaluate each integral or show that it diverges. And in part A, we have the integral from 0 to 3 of 1 over the square root of x dx. So why is this an improper integral? Well, my function, 1 over the square root of x, is undefined or discontinuous at this left endpoint of my interval, at x equals 0. So since my function has a discontinuity on our interval of interest, it is improper. And in order to define this, we have to make use of limits. So here we would be taking the limit as t approaches 0 from the right of the integral from t to 3 of 1 over the square root of x dx. And we know how to find a antiderivative of 1 over the square root of x. Now 1 over the square root of x, well, that's x to the negative 1/2. So its antiderivative would be x to the positive 1/2, or root x, divided by 1/2, or times 2. and then we are evaluating from t to 3. So we have the limit as t approaches 0 from the right of 2 times the square root of 3 minus twice the square root of t. And as t approaches 0 from the right-hand side, twice the square root of t will approach 0. So we're left with just the constant 2 times the square root of 3. So here our limit exists. It approaches this real number. So we would say that this improper integral is convergent to a value of twice square root of 3. Now, something that I want to point out with this example, if you think about the first part of this section 3.7 material, we had looked at an integral of the form 1 to infinity 1 over root x dx. And we saw that this value was infinite, which led us to a result known as the p-series test for improper integrals. So here we said, well, when our power p is less than 1, that implies that this integral would diverge. So we would say this diverges by the p-test for improper integrals. So why is it in this example that we just looked at, where we have the integral of 1 over the square root of x from 0 to 3, we had convergence? I thought this was divergent by the p-series test. Well, recall when we had introduced the p-series test, I said it only applies for these functions where our interval of integration is from some positive number a to infinity. In this example, we are not considering a type 1 improper integral. We do not have an unbounded interval. Rather, we have a discontinuous integrand. So here the p-test for these improper integrals does not apply. So be a little careful when you are applying that p-test for improper integrals that you're sure you're working with the correct type. Now let's look at another example. In our next problem, part B, we have the integral from 1 to 9 of 1 over the cubed root of x minus 9. So what is it that makes this improper? Well, our integrand is discontinuous when x equals 9. We would have division by 0. So since our function is discontinuous at that right-hand endpoint of our interval, that means this is an improper integral. And so to evaluate this, we would have to make use of a limit, as we did in part A. So I would be taking a limit here as t approaches 9 from the left-hand side of the integral from 1 to t of 1 over the cubed root of x minus 9. Now for simplicity, I might rewrite that as x minus 9 to the negative 1/3 power dx. So that's going to make finding my antiderivative a bit easier here. So we would have the limit as t approaches 9 from the left of the antiderivative of x minus 9 to the negative 1/3 would be x minus 9 to the positive 2/3 power divided by 2/3, or equivalently multiplying by 3/2. And then we are evaluating from 1 to t. So let's see what we get. We've got the limit as t approaches 9 from the left of 3/2 of t minus 9 to the 2/3 minus, when we evaluate at 1, we have 3/2 times 1 minus 9, or negative 8 to the 2/3. So that would be the same as the cubed root of -8, which is -2, and then squared, which would leave us with a value of 4. So simplifying a little, we have the limit as t approaches 9 from the left of 3/2 t minus 9 to the 2/3 minus 6, and then taking the limit as t approaches 9, this t minus 9 to the 2/3 power will be approaching 0, and so we are left with -6. So here we could say that our integral is convergent to a value of -6. All right. So let's look at another one. In part C, we have the definite integral from -1 to 1 of 1 over x squared. So why is this an improper integral? Well, my integrand, 1 over x squared, is discontinuous at 0. And 0 lies right in the middle of our interval from -1 to +1. So since this is an improper integral where our discontinuity is within the interval, we would have to evaluate this by splitting our integral into the sum of two parts, from -1 up until the point where we have our discontinuity, which was at 0, and the integral from our discontinuity at 0 up to the right endpoint, which was 1 over x squared dx. Now, each of these two integrals is itself improper because we have a discontinuity at the left or the right hand endpoints of these intervals. So each of these will have to be evaluated in terms of a limit. For our first integral, we're taking the limit as t approaches 0 from the left of the integral from -1 to t of 1 over x squared dx, plus the limit as t approaches 0 from the right of the integral from t to 1 of 1 over x squared dx. So finding an antiderivative, let's see what we have. The antiderivative of 1 over x squared is given by -1 over x, and we're evaluating in the first interval from -1 to t. And for our second integral, we have an antiderivative of -1 over x to the first power. This should not have been x squared in that first term. And we're evaluating from t to 1. So let's see what we have. For our first integral, we have the limit as t approaches 0 from the left of -1 over t minus, when we evaluate at x equals -1, we would have a +1, plus the limit as t approaches 0 from the right of -1 minus a -1 over t gives us +1 over t. And so taking the limit of each piece, let's see what we have. So for this first limit, as t approaches 0 from the left, this ratio 1 over t will become larger and larger. So if we're dividing by t and t is getting smaller, well, dividing by a smaller and smaller number will give us a ratio which is becoming infinitely large. Now here we had a -1 over t, but t was approaching 0 from the left, which means that we were working with negative values of t. So -1 over t is then a positive value. So the limit of this first function is going to be a positive infinity. And once we see that improper integral, this first improper integral diverges, I know that the entire integral is divergent, because in order for this to converge, we said both of these integrals in the sum would have to converge. So as soon as I see that one is infinite, I know that the improper integral I'm working with diverges. But for a little extra practice with limits here, let's consider the limit of the next term. So as t is approaching 0 from the right, the fraction 1 over t is becoming infinitely large. And since this was a right-hand limit, that means that the values of t are greater than 0, or positive. So 1 over t would be positive and is becoming infinitely large. So we have a limit which is becoming infinitely large in the positive direction. We would say that this integral is divergent. Again, as long as we know, or as soon as we know that either one of these two integrals in our sum is divergent, I know that the entire thing is divergent. We don't have to evaluate both parts there. So here we can say that this is divergent. Now, something that I want to point out with this last example is that we need to be a little bit careful when we're trying to identify an integral as improper or not. So if we were to consider this problem, and we did not recognize that this was an improper integral because we have trouble at 0, we might be tempted to try to evaluate this directly using the fundamental theorem of calculus by saying, well, the antiderivative of 1 over x squared is negative 1 over x, and we're evaluating from negative 1 to positive 1. So when I plug in x equals 1, I would have negative 1, and then I subtract what I get when I substitute in negative 1 for x, which would be a positive 1. So negative 1 minus 1 leaves us with negative 2. So we might say, well, our answer is negative 2, but this would be incorrect. As we just established using the definition of an improper integral, this value is divergent. It does not converge to negative 2. So what's the problem with that second solution? Why did this give us an incorrect value? Well, we were using the fundamental theorem of calculus here. However, recall that the fundamental theorem of calculus only holds if the integrand, that is the function that we're integrating, is continuous over our interval from a to b, which it is not here. We have a discontinuity at 0, which is why this fundamental theorem of calculus approach is not valid. We have to recognize this as an improper integral in order to get the correct result. So as a little word of warning here, when you see definite integrals on the homework or the second exam or final, always ask yourself first if it's an improper integral, if there is some discontinuity of your function within that interval, because if so, you cannot use the fundamental theorem of calculus.